And many of you are probably wondering about the term experimental metaphysics, if you're not familiar with that in my title. Isn't that an oxymoron? And I'll get back to that in a minute, but first let me also acknowledge my collaborators. And the talk today, I'll talk about a series of results over the last few years with various co-authors. And I'll present a general overview of these results. The first one being this paper from 2020 with a number of collaborators, Kokwei Bong, Fazad Ghaffari, Nora Tischler, and Jeff Bride were the experimental team in this work. Anibal Gutierrez Alacon, Yongchang Liang, myself, and Howard Wiseman were the theory team. All except for Yongchang are in Griffith. Yongchang is in Taiwan. Kokwei and Anibal were the joint student first authors in this work, and Nora and I were the joint corresponding authors. And in that paper, we proved what we call the strong no-go theorem on the Wigner's friend paradox, or we also called it the local friendliness no-go theorem. So in my talk today, I'll also refer to this 2021 paper with Howard Wiseman, where we discuss in more detail in what sense our no-go theorem is stronger than Bell's theorem, and give a broader picture of some of its implications. Also, I'll mention briefly this single author paper from that same year, where I discuss a particular type of resolution of the LF no-go theorem and some of its implications for cubism in particular. And I'll also give a brief outline of two more recent papers which address some different types of criticism of the original no-go theorem, and in different ways. The first is a paper that's recently posted on the archive with my student Marwan Hadra, where we prove a version of the theorem without using probabilities. And the other with Howard Wiseman and our collaborator Eleanor Riffel from NASA, where we reformulated in the strongest way that is suitable for what we think would be the ultimate experimental demonstration of its kind, which involves a human-level artificial intelligence running in a very, very large quantum computer. And this one, we were hoping would be out already today, but it's definitely going to be out in the next few days. So stay tuned for it coming out in the archive. Now, you might have noticed that the title of my talk has changed from what I was in the initial program. I had previously intended to move the title of just this last paper, but I thought it would be more interesting for this workshop to give a broader overview of the results. Okay, so going back to experimental metaphysics, the term was coined by Abner Shimony. So let me start with a quote from a paper that he presented in a 1999 meeting that was sponsored by the Vienna Circle Institute. It said, "Some nostalgic person in this gathering could say that the absence of a definitive adjudication between interpretations of quantum theory is a vindication of the general skepticism of the Vienna Circle regarding metaphysical interpretations of the natural sciences. That statement, however, is a case of bad logic. If one doesn't know which of two metaphysical theses is correct, but the two are not exhaustive, then that disjunction remains a non-trivial metaphysical statement. And the point is that all of these interpretations are constrained by the formalism of quantum mechanics and the body of experiments upon which it rests. In this sense, one can say, even at the present unsatisfactory state of our investigations, when a number of interpretations remain imperfect candidates for providing an understanding of quantum mechanics, that a disjunction of these interpretations is a non-trivial contribution to experimental metaphysics. Of course, it's desirable to sharpen the metaphysical implications of quantum theory by definitively eliminating some of these candidates." He also suggested that working on interpretations themselves would be a way forward in that, but I would, however, not focus so much on ruling out particular interpretations as such, but ruling out classes of candidate theories as the goal of experimental metaphysics is the most useful thing to do in that field. And the classes of candidate theories, I mean, defined by their satisfaction of general metaphysical hypotheses. So, for example, the most notable result of experimental metaphysics is Bell's theorem. And there are many different versions of it. There's many different ways in which you can derive Bell inequalities. And so for a review, I'll just point you to this paper from Howard Wiseman and I. So in our terminology in that paper, Bell's original 1964 theorem can be formulated as saying that there exists some quantum phenomena that violate the conjunction of these three assumptions: no superdeterminism, locality, and predetermination. So here in similar graphics, the arrows mean that the conjunction of the concepts in the incoming nodes logically imply the concept in the outgoing node. So the conjunction of these three metaphysical premises imply Bell inequalities, which have been shown to be violated by nature, and so it's represented by the black background. And so that means that because these violations have been observed with all the loopholes closed, essentially all the loopholes closed, that no physical theory can simultaneously satisfy these three assumptions. And this is a non-trivial metaphysical statement. And furthermore, we can be very certain that this statement is correct, even in fact, more certain than we are that any of our best physical theories is correct. Because after all, science can show when the theory is false by not being able to reproduce experiments, but it can never show that there won't be another future experiment that will demonstrate that it's false. So this is solid knowledge, it's solid metaphysical knowledge. So I can't find a place where Shimony gave a clear definition of experimental metaphysics. So just I think it's not necessarily don't want this to be an exhaustive definition, but tentatively I would define it as the study of the properties of physical theories themselves using methods of physics like mathematical theorems and experiments. And it has Bell's theorem as its most notable result. And if you're still suspicious about the term metaphysics, even if they qualify experimental, then consider this analogous term metamathematics, which is a perfectly adequate and completely accepted term to designate the field that studies the properties of mathematical theories themselves using the methods of mathematics, and which has Gödel's theorem as one of its most notable results, which shows that no mathematical formal system can simultaneously satisfy certain sets of metamathematical properties. And that field, and I think the term as well, was initiated by David Hilbert's program to put mathematics in solid foundations. Okay, so then returning to Bell's theorem and to better explain how our new no-goal theorems are a non-trivial contribution to experimental metaphysics. Let's return to Bell's theorem. As you probably know, it refers to a scenario involving two observers, Alice and Bob, who perform measurements on a pair of entangled systems, particles preparing some entangled state within space-like separated regions. The arguments and the terminology that I'm going to use will be largely, as in the previous paper that I mentioned, but also updated in this recent paper with Howard Wiseman. But some of the terminology and some ideas have also evolved since then, including through collaboration with our visiting student, Yila Ying. So just starting things off, we need to define the notion of an empirical phenomenon, which consists of a specification of a reproducible experiment, including a set of observable events corresponding to choices of experiments or interventions, here the variables x, y, and their corresponding outcomes, here the variables a and b. We specify any background requirements like spatial temporal relations between these events and preparation procedures, etc. And phenomena will be characterized by some empirically observable probabilities, which I represent with this curly p, involving the publicly observable empirical variables a, b, x, y. So, and in the class of phenomena that we are considering, it turns out that these conditional probabilities have the property that do not depend on how the interventions are chosen. For example, whether they're chosen by flipping a coin or using a random number generator or by the whim of the experimenter, these conditional probabilities are the same in a way. They define the phenomenon. So to derive Bell's theorem, also two background assumptions are needed, which are typically left implicit. And the first is what we call absoluteness of observed events or of observations. And in a previous paper that on this one, we call it macro reality, which is the assumption that any observed event is an absolute single physical event, not relative to anything or anyone. When some terms appear in small caps, that means that that's a concept that may be modified by other assumptions, and it's not intended as a definition. And we also need to assume that these events can be located in a background relativistic space-time, where we can talk about Lie cones, space-like separation, etc. So Bell's 1964 theorem can be reformulated with a bit more care as showing that there exists quantum phenomena that violate the conjunction of those three assumptions under the background assumptions of absolute events and space-time. And in the interest of time, I'm not going to show the formal definitions of the first two of these assumptions. I'll just refer to that paper for that. And that's because these assumptions are somewhat awkward to formulate and not particularly natural, as it turns out. And they can be replaced by a more natural assumption that we call local agency. So we'll only use local agency from now on. And that's the requirement that an intervention, and an intervention is supposed to be made in a manner that's appropriate for randomized experimental trials or a given phenomenon, can think of that as part of what it means to be an intervention, is uncorrelated with any set of physical events that are relevant to that phenomenon and outside the future Lie cone of X. And what it means for it to be relevant is that these events must figure in any complete explanation of the phenomenon according to the candidate theory against which we are evaluating this hypothesis. And to define predetermination carefully turns out to be a little bit more complicated. It's a bit of a mouthful. So I'm not going to read the whole definition either. It won't be particularly useful for the rest of the talk in any case. For the purpose of a typical Bell experiment, it's just essentially the requirement that the outcomes are predetermined by some variables in the past of the experiments in some reference frame, perhaps in conjunction with the choices of the experiment. So in a typical Bell scenario like this, we have the outcomes A, B, settings X and Y. We can consider a space-like hypersurface like this prior to all of these variables where some variables lambda are defined. And then predetermination implies that the probabilities for, say, outcome A, given the full specification of the lambdas and the settings X and Y, that's determined. It's with probability 0 and 1, and similarly for B. And local agency implies what there's two types of mathematical implications. One, which is an implication of what we call locality, and sometimes called parameter independence. And the other is the implication that from what we call no superdeterminism, sometimes called freedom of choice. The first type is that the probability of A, say the outcome A, given a full specification of the lambdas, does not depend on the distant choice of setting given X and Y, it doesn't depend on Y. And similar for B, doesn't depend on the distant choice of setting X. And the probability for these variables lambda do not depend on the choices of setting. So given these two, these imply constraints on the empirical probabilities, which are the Bell inequalities, which experiments have been found to violate. Now, so one of the initial responses to Bell's theorem, and one that is too popular today, is that, well, we may just give up the predetermination. After all, isn't quantum mechanics supposed to be indeterministic? But unfortunately, that's not enough, because as Bell showed in 1976, Bell inequalities can be derived from a weaker assumption, which is local causality, which is the requirement that if two space-like separated events, A and B, are correlated, then there is an event in the intersection of the past Lie cones, such that conditioning on that, the correlation is eliminated, the probability is factorized. And that, together with local agency, which plays the role of the assumption of freedom of choice or no superdeterminism, we can reach a contradiction with some quantum phenomenon the violated Bell inequality. Now, local causality can be thought of as the conjunction of two assumptions. One being Reichenbach's principle of common cause. Reichenbach was a philosopher, which there is no evidence that Bell knew about him, but local causality is essentially the conjunction of Reichenbach's principle of common cause, which just requires that if two events are correlated and neither is a cause of the other, then they must have a common cause that factorizes the correlation. And the other is the requirement that any causes of an event are in its past-like coins. So it's easy to see that the conjunction of these two is just exactly the same as local causality. And Reichenbach's principle also follows from this more general framework of causal models, for example, as formulated by Judea Pearl, which is widely used today in many areas of science, and including in quantum foundations. And in this framework, causal structure is represented as a directed acyclic graph. So here, the causal structure of the Bell scenario has this form where lambda represents a complete specification of the common causes. And one of the basic assumptions in that framework is the causal Markov condition, which implies Reichenbach's principle as a special case. In 2014, Ray Lau and I proposed to break down Reichenbach's principle further in terms of two independent principles, one that we call the principle of common cause proper, which is just the requirement that correlations must be explained by a common cause. And the other is the requirement that what it means for the common cause to explain the correlations is that conditioning on the common cause, the correlations factorize. In other words, the common cause must explain each of the events independently of the other. And the conjunction of these two, it's also easy to see, implies Reichenbach's principle of common cause. In that work, we also proposed using the quantum conditional states formalism of Matt Leaf and Rob Speckens, that this principle of factorization of probabilities could be replaced by the factorization of quantum channels, or more precisely of the operators that correspond to the channels from the common cause to Alice and Bob by the Choi-Minkowski isomorphism. And this allows us to keep the principle of common cause with a modified notion of causal explanation, which is what's done in a series of results, and more notably one by Costa, Fabio Costa and Sally Shrapnel, and also by Allen et al., more recently John Barrett and his group, who proposed various frameworks for quantum causal models, of which this is an incomplete list of contributions. And some of the key features of these is that they allow for causal discovery, they're compatible with relativistic causality, and they're reduced to classical causal models as a special case. So it provides at least a resolution of part of the puzzle of Bell's theorem, which we call the easy problem of Bell, which is the problem of giving a causal explanation of Bell correlations. But it doesn't provide a resolution of what I would call the hard problem of Bell, which is the measurement problem itself, which we will get back to in a minute. But just to complete that picture, if we now introduce this assumption of independent interventions, which is the requirement that intervention has no relevant causes, that is, it can always be chosen via variables that do not have causes among, nor share a common cause with any other of the other experimental variables, then the conjunction of these three assumptions imply local agency. And putting back the other errors, now with the dashed and the full lines representing the two versions of Bell's theorem that I have discussed, we can conclude that the violation of Bell inequalities can be resolved, can be accommodated by rejecting the correlating explanation as well as all the concepts in red, while keeping all the other ones. And this is what is done essentially in quantum causal models. And it is also analogous to a resolution by Shimony, a proposal to resolve Bell's theorem, which he proposed as a peaceful coexistence between quantum mechanics and relativity, which was rejecting the assumption that he called outcome independence, which essentially follows from the correlating explanation, while keeping parameter independence, which is the notion that previously we called locality, essentially, which is part of local agency. So it would be great if we could stop here, but our new no-go theorem poses a challenge to this resolution. So let's leave Bell's theorem aside for now and consider Wigner's friend paradox. It was proposed in 1961 by Eugene Wigner. He said that the wave function is only a suitable language for describing the body of knowledge gained by observations, which is relevant for predicting the future behavior of the system. For this reason, the interactions which may create one or another sensation in us are also called observations or measurements. It is natural to inquire about a situation if one does not make the observation oneself, but let someone else carry it out. One could attribute a wave function to the joint system, friend plus object, and the joint system would have a wave function also after the interaction, that is, after my friend has looked. So we represent this scenario where the friend is in some isolated lab and receives some system S in some state psi and measures it on some fixed base, obtaining some outcome C here. And subsequently, Wigner can measure the whole contents of the lab, including the friend. So let's say that Wigner describes the friend initially as being some ready state R. And what it means for the friend to measure S, say on the computational basis, is, of course, that if S is initially in the state 0, the friend state will change to reflect that state to some state O0, and the state of S will be left unchanged if it's an ideal non-disturbing measurement. And similarly, if the state of S is initially 1, state of friend will change to reflect that state to O1. Now, if the system is in some superposition of basis states, then textbook quantum mechanics says that after the friend's measurement, the system, and of course the friend's measurement record, will be in one or another of those states with a probability given by the Bond rule. But on the other hand, if the friend is isolated from the external environment, then according to the unitary evolution postulate Wigner from the outside can describe the joint state of the system and the friend as and the friend and everything else inside the lab as an entangled superposition, as in the state 3. And Wigner concluded that this is a contradiction because the wave function 3 describes a state that has properties which neither 1 nor 2 has. And this is in a nutshell the measurement problem. Now, you may avoid this conclusion if, say, you consider those quantum states as describing not states of reality, but states of information. Then 1 and 2 could be simply interpreted as describing situations where the friend has more information than Wigner. So it could be no more a contradiction than if we were talking about a coin toss and the friend assigned probability 1 or 0 to whether it landed heads, say, while Wigner assigns probability a half each. And furthermore, this is a contradiction in the textbook formulation of quantum theory, but can we have a theory-independent statement like Bell's theorem, which doesn't assume anything specifically about quantum theory, such as the ontology of the quantum state? So, we arrived at extended Wigner's friend scenarios, and some prior results include this result from Frockiger and Renner from 2018, which is the more commented one of those. Which uses epistemic model. It can be formulated in terms of epistemic model logic. One drawback of that result is that it's not theory independent in the sense that it contains assumptions specifically about quantum theory, like Wigner's original argument. And it's also not an idealized experiment, so it's not testable like Bell's inequalities. Our work is based instead on the scenario introduced by Czeslaw Bruckner in this 2015 paper and also used in this other more recent paper. And the scenario is as follows. Now we have a bipartite version of the Wigner's friend thought experiment with two friends, Charlie and Debbie, and their respective super observers, which outside of the labs and are called super observers because by assumption they can perform close enough to arbitrary quantum operations on the whole contents of their respective friends' labs. So friends also called the observers. So Alice and Bob have, so friends perform a fixed measurement and obtain outcomes C and D. Alice and Bob perform measurements with choice of setting X and Y and outcomes A and B. Now, if Alice chooses x equals 1, the protocol goes, she will simply open the box, so to speak, and ask Charlie what he observed, and then set her outcome A to be equal to Charlie's outcome C. And if she chooses some other measurement setting, say 2 or 3, she'll perform a different measurement. And any such measurement can be implemented without loss of generality as far as the relevant outcome statistics are concerned, by reversing the unitary evolution that entangled Charlie with the system, and thereby erasing Charlie's memory in the process, and then proceeding to perform a measurement on the system alone in some other basis, potentially. And the system has now been returned to its original entangled state with the distant lab. And the various events in this scenario can be represented in this space-time diagram. So we call local friendliness the conjunction of these two metaphysical hypotheses, absoluteness of observed events and local latency, which I introduced before. And from these, we derive the local friendliness inequalities in analogy with Bell inequalities, which are constrained on the observable probabilities by Alice and Bob. And we show that they can be, in principle, violated if a certain technological assumption holds, not a metaphysical hypothesis. The technology assumption is that a super observer can perform close to arbitrary quantum operations on an observer and its environment. It's not necessary, even though here we're talking about quantum mechanics, the only important thing about this is that the right kinds of statistics can be obtained that violate the local friendliness inequalities in a scenario of this type, in much the same way as with, say, with Bell inequalities. And we perform a proof of principle experiment that demonstrates these violations. So let me walk through a little the proof briefly. The assumption of absoluteness of observed events, it implies that in each run of the experiment, all the observed events that are observed by any of the observers, which includes all of these variables here, A, B, X, Y, C, D, they must have a well-defined absolute value. There is an observer independent value. And so this implies that there is a joint probability distribution for A, B, C, D, conditional on the choices X and Y, which must be consistent with the marginals that are observable by Alice and Bob. And by the construction of the scenario, when X equals 1, Alice sets her value to be equal to C, and then Y equals 1, B equals D. And here, in the following equations, they are interpreted as holding for all values of the three variables, of course. And I emphasize that this is not saying, not contradicting the Paris's dictum that unperformed experiments have no results. It's just saying that experiments that are performed by some observer have absolute results, observer independent results. And also, this is a subtle issue, but very important. The existence of this joint probability distribution for the observed events does not imply that there is a joint probability distribution for the outcomes of all observables, independently of whether or not they're measured. This is a weaker requirement. Now, local latency in turn implies these two conditions. One, that the probability, say, of Alice's outcome, conditioned on C, D, X, and Y, is independent of Bob's distant choice, and similarly for Bob, it's independent of Alice's distant choice of setting. And the probabilities for the outcome C and D of the friends are independent of the probabilities, independent of the choice of setting X and Y, which can also be thought of as the implication of locality and no superdeterminism. So now these assumptions imply constraints on the possible correlations that are observed by Alice and Bob. And these correlations form a polytope in a given scenario, whose facets are associated with linear inequalities, which we call the local friendliness inequalities. So the local friendliness polytope is a union of this green set, which is the local hidden variable polytope, the Bell polytope, with the orange set. So this is an actual 2D cut on this multidimensional set of correlations for the case where we have three settings and two outcomes per site. And so one thing to note, so this is the local invariable polytope, and this is the local friendliness polytope, includes the orange ones. The red line is the boundary of quantum correlations. So then here what we can see is, say, the local friendliness inequalities can be violated by quantum mechanics, say here and there. And also there are some quantum states which violate some Bell inequalities, but do not violate any local friendliness inequalities. It's not directly implied by this cut, but we prove this by deriving all of the local friendliness inequalities for this scenario. There's 932 of them, and showing that there's some correlations that violate a Bell inequality, but do not violate any local friendliness inequality. And this is a reflection of this important fact that the inequalities, the local friendliness inequalities, that derive from strictly weaker assumptions than those needed to derive a Bell inequality. So their violations in a properly specified scenario have strictly stronger implications than Bell's theorem. And we also performed a proof of principle experiment to test the violation with polarization entangled photons. And here the role of the friend is played just by the path that this photon takes after a polarizing beam splitter. The photon polarization becomes entangled with the path, which can be interpreted as the path measuring the polarization. And Alice opening the lab and asking Charlie what he saw corresponds to Alice putting a mirror on the path to deflect the beams and then detect the path. There is detecting Charlie's memory, so to speak. And the other measurements are performed by unitarily reversing the entanglement between the path and polarization and measuring the photon on some different bases. I'm not going to get into more of the details of the experiment. I'll just refer you to the paper. The bottom line is that the experiment violated local friendliness inequalities, several various of them, by more than 17 standard deviations in some cases. So returning to our concept diagram, so we can now formulate the local friendliness theorem in this way, that there exists quantum phenomena that violate the conjunction of absoluteness of observed events and local agency, or equivalently of these more fundamental assumptions. And the important thing to note is that we can in principle reach a contradiction now, starting with a strict subset of the assumptions that are needed to derive a Bell inequality. And in particular, the type of resolution of Bell's theorem that I was mentioning before, which is what is done in quantum causal models or in Szymanow's peaceful coexistence, cannot resolve the LF no-goal theorem. So it's a non-trivial contribution to experimental metaphysics. And here I put in gray to indicate the fact that even though the inequalities have been violated in this experiment, there is an open question whether they can be violated with more convincing, more complex observers. So now I'll discuss two possible objections to the theorem, and briefly present two new theorems that address these objections. And the first is an objection that also applies to Bell's theorem, which is that one may be suspicious about the use of probability theory in the proof. Say in the first equation here that we use for the implication of absoluteness of observed events. These probabilities on the left-hand side are empirically observable, publicly observable by Alice and Bob and whoever else wants to look at them. But the ones on the right-hand side, they are theoretical probabilities. They are implied by the existence, which is implied by absence of observed events of these well-defined values for these variables C and G. But perhaps even if we admit that this assumption might be true, perhaps because these are not directly observable by anyone, these probabilities may not converge, or for some reason or other, standard probability theory fails and this equation doesn't hold. Even though the statement of the assumption might be true. And this was in fact a question that was raised by Jacob Brandes when I gave a talk about this work at a Harvard Foundations of Physics workshop that he was organizing back in 2020. And Matt Leifer also suggested that it could be possible to find a proof without using probabilities. And that motivated this work. So that's the results that we have recently posted on the archive. So here we use absoluteness of observed events as was previously formulated, but we replace local agency by a strictly weaker metaphysical hypothesis, which we call possibilistic local agency, which doesn't refer to probabilities, but just to possibilities. And here in this talk and this paper, when we talk about possibilities, we refer to physical possibilities, not to logical or metaphysical possibilities. So then this assumption, informally speaking, it says that an intervention cannot affect the possibilities of events not in its future-like cone. But a more precise way of stating it is that if a set of events is possible, then for any intervention Z, not in the past-like cone of any of the events, in E is possible in conjunction with any value for Z. Now the possibilistic collapse of a phenomenon, so we use the diamond, the symbol from modal logic, to represent the proposition that an event is possible. In this case, the string of symbols says that can be read as saying that the conjunction of E and Z is possible. And in the context of a probabilistic theory like quantum theory, we say that an event like this is possible if and only if the probability of E given Z is non-zero. And local agency implies possibilistic local agency, but the converse doesn't hold. Now, suppose we have the following possibilistic phenomenon, where it's possible that, say, the variables a, b, x, y take the values 1, 1, 2, 2, as in the first line, but it's not possible that they take the values 0, 1, 1, 2, etc. So now absoluteness of observed events implies that C and D must have some value, some well-defined value in every possible world. So if this set of values is possible, then it's possible to have this set of values in conjunction with some value for C and D, where I'll denote the lowercase c and d as representing a particular unknown value for these variables. So now consider this set of events which are not in the future-like cone of X, the ones in green. So if this set of events is possible, then by possibilistic local agency, they must be possible also in conjunction with a different value for X, say X equals 1. And by absoluteness of observed events, A must have some value, let's call it little a, although possibilistic local agency doesn't require that it be the same as it was before. But by the construction of the protocol for X equals 1, A must be equal to C, whatever C is in this case. But we don't actually require that it must be the same, but just that it's possible that a value of A, we just require this proposition that it's possible that a value of A be the same as C together with the other values of the other variables already specified. And now looking at the second line, which says that this set of events is not possible, then we find that then this line here, with this set of events being possible, that means that C cannot be equal to 0. And so we conclude that C cannot be equal to 0. And by a similar argument, by symmetry, we find that D cannot be equal to 0. And also a similar argument now using the last line here, we can show that neither C nor D can be equal to 1. And then we reach a contradiction because now there's no possible values for C and D, which are consistent with this possibilistic phenomenon, in particular this first line here, which says that these sets of events is possible, but we conclude that it's not possible in conjunction with any particular values for C and D. So that's the contradiction. And we can show that this can be realized in an experimental Wigner's friend scenario when Charlie and Debbie initially share an entangled state prepared in the Hardy state, the type that leads to a proof of Hardy's paradox. And we show that there exists some measurements for Charlie, Debbie, Alice, and Bob, such that this possibilistic phenomenon is realized as the possibilistic collapse of the probabilities for these measurements. I'm not going to go through all the details here. You can read through in the paper. Okay, so now the second objection So these address the first objection about probability theory. So we can prove a no-go theorem without using probabilities, and in fact, using even weaker assumptions than before. And incidentally, these the Hardy state and these correlations are similar to the ones used in the proof of Hockenheim and random paradox. So that shows an interesting relation between the two. Now, the second objection is more substantial, which is that the no-go theorems I have presented so far make reference to observers or observations, but give no criterion to determine when a given experiment contains an observer. So talking about our experiment, is it a convincing experiment? Well, we call it a proof of principle because it involves very simple friends. The friend has one bit of memory, so to speak. So it doesn't realize Wigner's original thought experiment, which involved a conscious friend, obviously. Well, perhaps not obviously. If you're a panpsychist, you might say that it does. But on the other hand, it's a mathematically precise representation of the scenario, in the sense that the observer degrees of freedom and the system degrees of freedom are represented by tensor factors of the Hilbert space, and the measurement leads to entanglement between the observer and the system in the appropriate way. And if you consider that any physical system can be thought of as an observer, then this is good enough. For example, Andrea Di Biagio and Carlo Rovelli said in this 2020 paper, remarkably, these inequalities have already been shown experimentally to be violated for the case in which Wigner's friend is a single photon. One might be tempted to dismiss the result on the grounds that photons do not generate facts, but this opens the question of deciding which systems give rise to facts. But we are not committing to anything. An experiment could fail to validate the inequalities at some level, and that's for nature to decide, but the question is at what level, and why would that be? And to answer that question, we need to answer the question of what is an observer. So let's consider some potential responses. One could say there's no such thing as an observer, there's no such thing as an observation, but that seems like a non-starter. Physics is an observational science. How do we obtain evidence for anything? We must reproduce the most basic facts of our experience, which is that we observe things. And that's where we get our evidence from. One may say that it requires an irreversible act of amplification, which is what, according to Wheeler, Bohr was opinion of Bohr. One issue is that it's a slippery definition. How do we know that a process is truly irreversible and not just irreversible given our current technological limitations? That is the question that we need to answer. To just say that it is irreversible is just to state that by definition, and it's not exactly a definition that is useful in any sense. There's no point in which we can know that a process is irreversible, and not just because we are not able to reverse. In particular, for all we know, our observations are compatible with quantum mechanics being universal, and unitary evolution being universal, and the impossibility of reversing things being due to decoherence and due to our inability to reverse, not a fundamental limitation. And our answer could be that the irreversibility comes from some objective collapse, like an objective collapse model. And that might be true, but it may actually not be enough to resolve the no-go theorem. And I'll return to that quite later, but quickly, it's just essentially because an objective collapse theory may not prohibit universal quantum computation. So one criterion that I think most people will accept as being a sufficient criterion, even if not necessary, is that an sentient being with the same types of impressions and sensations as I, and that's a quote from Wigner, is an observer. But then what type of sentient observer could be unitarily reversed? The answer is an artificial intelligence implemented on an enormous fault-tolerant quantum computer. And that's the topic of this paper in preparation, which should come out very soon. So very quickly, the experiment now needs only one friend, Charlie, who is a human-level AI running a huge future quantum computer. Charlie shares a singlet with Bob, and he's instructed to observe the qubit in the Z base and think about the outcome. And Charlie communicates these results with some message to Alice back on channel. Alice can choose to read the message or return to Charlie, reverse the computation, and perform a different measurement. There's some other details which I'm glossing on. And then Alice and Bob estimate the probabilities A, B given X, Y. And now the conjunction. Yes? The conjunction of these assumptions then is a contradiction, local agency, as I defined before, and three new assumptions. The first being physicalism, that any thought supervenes upon a physical process in time, in the space of the brain or other information processing unit. Ego absolutism, the assumption that my communicable thoughts are absolutely real. It could be replaced by a human's communicable thoughts are absolutely real, but this one is a little bit more impactful to think about. And friendliness, now there's an assumption actually called friendliness, which is if by open-ended communication, an independent party displays cognitive ability, at least on par with my own or with a human, then they have thoughts, and any thought they communicate is as real as any communicable thought of my own or of a human. And so if we assume that, well, the technological assumptions, which I'm here in brown, that human level artificial intelligence is possible. This is not a metaphysical assumption. It's an assumption about what may be technologically possible in the future. And that universal quantum computing can be done at arbitrarily large scales and very fast. So then if we assume physicalism, ego absolutism, and friendliness, then that implies that these communicable thoughts of the friend implies the same implications as absoluteness of observed events, which then in conjunction with local latency allows us to derive the local friendliness inequalities in short. And yeah, so the advantage of this formulation is that it has a clear, although very hard, experimental goal and has no ambiguity about when the inequalities are violated. No criterions left to be filled about what constitutes an observer. And each of these assumptions are rejected by at least one approach or interpretation to quantum mechanics, which is indicated by the diagonal, the ends on the diagonal in this table. And the theorem also clearly shows that the position that quantum mechanics needs no interpretation is untenable because it does not clearly reject any of these assumptions. But I'm not going to get into all the details of that because we're short on time. Just to conclude, just want to tell a little story, which I don't know if it's apocryphal, but it's a nice story. That Michelangelo, when he was asked about how he sculpted David, he said, I just removed anything that was not David. And I think of similarly, the landscape of possible physical theories is this raw block of marble. And the tool of experimental metaphysics is this chisel with which we can carve out regions of the landscape that do not represent our world. And it may well be that it's impossible to reduce this block to a point, this one single theory of everything. There may well be always many different metaphysical theories and interpretation describing the same observations. But we can hope that once we remove all the non-physical ones, at least, what remains forms a beautiful picture. Thank you.
Questions? Anyone from either Zoom or in person? Donald Hoffman?
If Chris Fuchs were here, would you say this was a trouble for his theory or not?
No, he certainly would not say. In fact, I've written a paper, this one here, where I strengthen an argument that I made for cubism many years ago, about 2007. But yeah, in fact, it can be in some sense be taken as an argument for cubism. If you want the details, you can have a look at that paper. So it's certainly not a trouble for cubism. I wonder why you would say that.
Sorry, did you say argument for cubism? Can you say a little bit more?
Yeah, so roughly speaking, that So cubism is often criticized as being akin to solipsism, right? In part because of the personalist view of quantum states. So these no-go theorems, if you want to stick to the assumption of local agency, which is required by relativity, then the implication is that we must reject absoluteness of observed events. But also the extra assumption there is that something like what we call friendliness, that we attribute the same reality to the friend's observations as to our own. And so taking that assumption, which is really sort of the opposite of solipsism, is a kind of Copernicanism, we conclude that we require a form of perspectivalism, that we require relative events. Cubism is not a single interpretation that has that property. You can also say average or relational quantum mechanics, but at least we arrive at that conclusion by requiring a form of Copernicanism, and so that I think that gives, reduces the strength of the criticism that cubism is solipsistic.
I'm not sure I'm not sure I see how it reduces it. I mean, if the ultimate end of that is that every event is perspectival, then each observer has their own perspective, which is not linked in any way to anyone else's, and that is solipsism, right?
No, there's no point that this is required that there is not linked in any way to anyone else's. Just that there isn't an absolute perspective which fully captures all of the perspectives at once. There's no requirement that there is nothing that links those perspectives. And of course there is.
But I'm saying you have no requirement that there is anything that links things, right? Where does that come from?
Well, what I'm saying is that there isn't, well, for one, we have good reasons to think, and we all bet on the idea that, say, if we were to be in the position of the friend, we would, we would expect to see this or that observation. We would advise the friend to bet according to the bond rule. We would expect to see the same outcomes as the friend if we are observing the same things, and there's all kinds of reasons why we would expect these things. It's not like there's no requirement that we are each seeing completely different worlds, and there's no matching between these worlds. In particular, communication between observers leads to agreement about lots of things. So yeah, there's no requirement that we all live in completely separate solipsistic world. It is just a relaxing of the idea that all of our observations from all possible perspectives can be represented as from a single God's eye view that fully captures all these perspectives. But from
nothing
that idea to the idea that there's no connection between the perspectives, there's a huge gap.
David Chalmers?
Yeah, could you just, Eric, could you show the that table at the end again? The different views and what they deny. Yeah, I was interested to see that Calvin's in my model is the only one there that is listed as denying universal quantum computing. I mean, I can see why we're there, because if you say that collapse comes in at a certain level, then you won't get universal quantum computing. But isn't that also true of most other collapse accounts? That basically all of them are going to say that the quantum computations are going to collapse with very high probability and at a certain scale. So they will also deny UQC.
No, and this was pointed out separately to myself and to Howard by different people. To Howard was.
I can't hear you, Eric. Can you speak more loudly and clearly?
Sorry, yeah. So the short answer is no, and the reason is quantum error correction. If the collapse doesn't happen quickly enough, that it prohibits quantum error correction from being realized, and there's all evidence to suggest that it doesn't, then we would be able to correct quantum computations arbitrarily and perform universal quantum computation. There'll be, physically there'll be collapses happening all over the place, but at a logical level, the quantum computation can be realized. And for realizing this experiment, that's all that matters.
I don't see why that doesn't also apply to our view. If it's, it's probabilistic collapse, if we've got enough error correction, we'll stave off those probabilities and render them arbitrarily low. And I think that would also apply.
Yeah, I think the reason that is
Penny's collapse would also apply to at least our kind of consciousness collapse. Maybe not to an absolute threshold collapse, but would apply to probabilistic collapse.
I think the reason that is that if human level AI is true, and now we are running a universal quantum computation that will lead to a superposition of observer states, then your theory would say that that would collapse, and that should happen regardless, independently of, there's in a way that there should not be possible to error to correct.
And I'm thinking error correction here might consist in having like a zillion copies of the same AI system, and maybe a zillion minus one of them will collapse in a certain period probabilistically, but one just has to keep going, and then you'll get universal quantum computing.
It seems to me that once you say that it's a conscious AI, human level AI, then by your own definition, it must have enough complexity to trigger collapse, right?
But probabilistically. The point is that on Kelvin's and my version, there's a certain probability of collapse, but it's tricky because it's continuous collapse.
But universal quantum computing doesn't mean that it has to be scalable, which means that you can't have some exponentially small probability of succeeding. It has to be that you can build a machine that with you make it big enough and it's essentially deterministic.
I think if you're allowed to add arbitrary amounts of error correction, then likewise in these cases we could add arbitrary amounts of multiple copies of the system, so that one of them doesn't collapse.
I would say that if that were possible, then that would demonstrate that the theory is false, and we're here assuming that the theory is true.
Why would it demonstrate the theory is false? Again, it's a probabilistic collapse.
You can't all have Y's,
What's it?
One, no.
No, because we would be able to.
I think if we go that way, that's going to have to deny one of the others.
In a situation where we'd be able to not probabilistically, but with deterministically maintain this superposition of this conscious observer. So the theory would not be doing the job that it's designed to do.
I guess that depends on what the job is that it's designed to do.
Sure. Yeah.
I mean, you can't maintain a superposition of different states of a AI by just by just having multiple copies. You need to do quantum error correction for exactly the same reason that you can't get a scalable quantum computation by just doing multiple copies of the quantum computation without error correction. So you need to error correct.
Yeah.
You need to do quantum error correction.
Is there a reason why that won't work in this case?
Can I comment on that?
There's a reason why that won't work. It's because necessarily, I think the states that the states that you have to generate to do scalable quantum error correction have large phi, basically. Right. So the collapse is going to happen. The collapse is going to happen quickly, more quickly as you build these.
So large phi here is disanalogous to intuitively for a spontaneous collapse theory. You have systems with large mass, which are analogous to systems with large phi.
But you see,
in our method, what's the disanalogy here between phi and mass?
Quantum computation, the individual constituents of the quantum computation mass density of the quantum computer can be extremely low, right? I mean, so you can have millions and millions of qubits with barely any mass, whereas you can't have low complexity if you're going to do universal quantum computation. You necessarily, even if you just do something like a random quantum circuit, error corrected, it will have huge phi.
Okay. The mass will get high, but the mass density will stay low, and that's what matters.
Yeah.
Could I make another comment on that?
Go ahead.
Another perspective that, so quantum error correction works when you have local errors, basically, and spontaneous, like standard spontaneous collapse theories just postulate local errors, like they're microscopic events. But a consciousness causes collapse is saying that there's some global state of the whole quantum computer which is very complex or has consciousness or something like that. And that's the thing which decoheres. And that's exactly the sort of extremely non-local type of error model that quantum error correction cannot correct.
Right.